So this is the merged talk of two of my joint work. The first one with Cambyse from Technical University of Munich. The second one is with Marius Junge from University of Illinois and Haojian Li from Baylor University. So these two talks are a solution to the same problem, but from different approach. So the topic we're going to talk about is quantum Markov semigroup. And briefly speaking, a quantum Markov semigroup is just a continuous semigroup of channel. More precisely, we want for each time t, this semigroup map is a CPTP map. And when we compose PT with PS, we get the P at the time S plus T. This is the semigroup property. And then we also want this process is continuous with respect to the time. And this object has been long studied in physics literature under the name master equation, or later is called GKSL equation, named after these four authors, Grorini, Kozakowski, Sudasen, and independently by Lindblad, they characterized the generator of such quantum Markov semigroup. And you can see this generator L, there is one part with this unitary involution given by a Hermitian operator, and the other parts given by some interaction from the environments that's modeled by this Lindblad operator belongs to the B of H. And this is a quantum analog. This will give the quantum analog of the continuous time Markov chain. And it models the evolution of more open quantum system. As we see, this part goes beyond the unitary evolution picture of the closed system. So let's first see two basic examples. The first one is the depolarizing semigroup. If we choose a fixed quantum state, the depolarizing semigroup will send in every state rho to e to the minus t times rho with this probability, and then with the rest of the probability sending it to the fixed state sigma. When t goes to infinity, this semigroup will just sending everything to the fixed state sigma, which is called depolarizing. And another common thing quantum Markov semigroup is the dephasing semigroup. If we consider we have the density operator written in a specific basis, a dephasing semigroup will send all the off-diagonal entries to e to the minus t times it, so with the exponential decaying factor, and it will keep all the diagonal entries as they are. So in the limits t goes to infinity, this will just send every matrix to its diagonal part, which models the decoherence process. So with these two examples, we can talk about some notions. First, we say a state is an invariant state if it's fixed by every semigroup map. And we say a semigroup satisfies the detailed balance condition if the semigroup map is symmetric with respect to the state inner product, state-weighted inner product, as follows. And under the detailed balance condition, the semigroup will basically get rid of the unitary involution part where only has a dispassive dynamic. So for every state, initial state rho, it will eventually send it to invariant states. That's this, and this invariant states is basically the projection of the initial state onto the space of invariant states. And this E is also called continuous expectation, but you can just think as the projection onto the invariant states. A very relevant question is to consider how fast does such a decoherence process happens. And we can see here that for the first example, that this depolarizing semigroup has only one unique equilibrium state, one unique invariant state sigma. And for the second semigroup, we can have multiple invariant states that can list on the diagonal. So the first semigroup we call is primitive. The second semigroup we say is non-primitive. So in terms of characterizing how fast the convergence happens, a common quantity to study is the mixing time. Let's consider we have a semigroup on the matrix, D by D matrix algebra with detailed balance condition. Then the mixing time is the smallest time t, such that for every initial state, the semigroup at time t will sense it to like close enough to the its equilibrium states or its invariant states. And the standard tool to derive a mixing time is called spectrum gap, which is basically the gap between the zero eigenvalue and the positive eigenvalue of the negative generator in the Heisenberg picture. And you can also express it as the using the weighted L2 inner product, which is given as follow. But basically, this is equivalent to say the semigroup distance to its equilibrium in the Hilbert-Smith norm will decay exponentially fast with the gap as the rates. And moreover, it will imply the mixing time is controlled by one of the gap times the log of the inverse of the minimal spectrum of the invariant states. So it gives the estimates of the mixing time. Another powerful tool to deriving mixing time is called the modified logs of inequality, and this is about the quantum relative entropy, which is defined, just recall its definition, equals to, for two-state rho, and sigma is equals to trace rho log rho minus rho log sigma. And we want to describe a similar exponential decay property for the relative entropy from the semigroup involution to its equilibrium, that is decay exponentially fast. And this is exactly characterized by the modified logs of inequality. Here we're introducing a form for the non-primitive case that's first considered by Bardet. That is stated that the lambda, the parameter lambda, times the relative entropy from rho to its continuous expectation is controlled by this entropy production term, which is defined to be the negative trace, the generator acting on rho times log rho minus log sigma for all initial states rho. And here, this entropy production quantity is exactly the negative derivative of the relative entropy with respect to time. And by this property, by this equation, it's easy to see that these two, the modified logs of inequality is basically equivalent to the exponential decay of entropy convergence. If you take a derivative of the entropy exponential decay of entropy convergence, you get the modified logs of inequality, or you integrate the modified logs of inequality, you get the entropy exponential decay. So in short, we will just say the modified logs of inequality as MSI, and we denote alpha MSI as the optimal constant such that this inequality holds. And immediately one can say the MSI constant is upper bounded by the spectrum gap up to normalization constant 2. But on the other hand, one can see it will imply a stronger estimate for the mixing time. That's the mixing time, the time t, that's the initial state is close enough to the equilibrium, is upper bounded one of the MSI constants times log the inverse of minimal spectrum of sigma. So this is implying a stronger mixing time, a rapid mixing. So important property for the MSI constant for classical system is the tensorization. It's stated that if we consider the MSI constants for the tensor product semigroup, it's always equal to the minimum of the MSI constant for each individual semigroup. So this is a nice property that we can derive the MSI constant for a large composite system from individual subsystem. Is of course we also want this holds in the quantum system. Nevertheless, this property is largely unknown for the quantum case, and if we allow the semigroup to take the non-primitive semigroup, we even know this tensorization property fails for quantum Markov semigroup. The counterexample is actually just the qubit defacing semigroup, qubit depolarizing semigroup, that it is known by Castorinaro and Tam. That's the optimal constants for this for this depolarizing semigroup is 2. But with Mike Bryan and Marius Junge, we find that if you tensor this qubit depolarizing semigroup with another with identity on another qubit system, the optimal constant has to be strictly less than 2. And this strictly less is of course caused by the entangled states. And motivated by this, we're introducing a stronger notion of modified Logarithmic inequality, that we say a semigroup satisfies lambda complete Logarithmic inequality. In short, we will say it's the complete, so it's the CMSI. For positive lambda, if the semigroup tensoring with identity on an environment system satisfies lambda MSI, just the entropy exponential decay property, for all environments dimension. So this is a strong property that's not asking the semigroup itself has good convergence, but also is coupled with the environment system. And then we can define the optimal CMSI constants as basically the informal of the MSI constants, but consider the generator tensoring with identity on environments. It turns out that this stronger definition satisfies the tensorization property in the quantum case as we want. But on the other hand, it's actually a priori a question as whether this stronger definition can be held for large class of examples, because if we take an informal here, there's a possibility that when n goes to infinity, this constant goes to 0. So then this definition becomes trivial. And the main result of this talk that we want to present is that this is not the case. So in the joint work with Marius and Haojian, and independently another work with Cambyse, that we show that for every finite dimensional quantum Markov semigroup satisfy this detailed balance condition, then its complete modified Logarithmic constant is strictly positive. So it's not trivial. So then the interesting thing is that these two independent work approaching this problem from completely different ideas. So in the rest of the talk, I want to show you a sketch of the proof. So the first approach is in the joint work with Cambyse, that we use this concept of quantum chi2 divergence. If we are given a density operator, we define rho to be, this density rho weighted L2 norm as follows. As we take the norm square as the trace inner product of x star to x, but we are inserting this 1 over rho plus s. S is a scalar. We inserting this multiplication from two sides, and we integrate s from 0 to infinity. So you may wonder why is this in this form. First, let's note that if we just integrate the weight parts, we integrate rho plus s inverse square from ds 0 to infinity. This is nothing but rho inverse. That's the reason why we write here a rho inverse weighted. And this quantity is actually very relevant. First is the quantum Fisher information in the sense that it takes the second order directional derivative of the relative entropy. Moreover, if we take this weighted norm to rho minus sigma, a difference of two density operator with weight to one of them, with the weight to the second, then this is a special case of quantum chi2 divergence. And if back to the classical case, what's the chi2 divergence is nothing, if for two probability measure, a chi2 divergence is nothing but the variance of a Radon-Nikodym derivative with respect to the second measure. So that's the classical Chi2 divergence. And the key lemma we're going to use about this Chi2 divergence is as follows. Suppose we have two states, and the state rho is marginalized by state sigma up to a constant c in the matrix order. Then we can compare the weighted norm of rho inverse and sigma inverse for the same vector x. And in a reverse order, because the weight is the rho inverse, when rho is less than sigma, then the rho inverse is greater than sigma up to a constant. So ideally, this inequality is very natural. And then other property is that we can have the relative entropy is two-sided control by this quantum Chi2 divergence. For the upper bound, it's just the relative entropy just less than the quantum Chi2 divergence by the constant 1. And the lower bounds, we're losing a constant explicitly depending on this this constant c decide the matrix order. With this key lemma, the proof is actually simple, which you can see I squeeze this in just one page. We consider a simple case that the semigroup is trace symmetric. In that case, the negative generator is just a sum of a square for this dj operator, and each dj operator is nothing but the commutator with the Lindeblad operator we mentioned in the first page. And as we know, a commutator is a derivation in the sense is that it satisfies non-commutative Leibniz rule, and we can use this property to rewrite our Fisher information. We start with our Fisher information in a symmetric case, which is just trace of L rho log rho. And we use L is just sum of square of dj. We can write it as the inner product of dj rho and dj of log rho. And then we can use non-commutative chain rule. We are taking derivative to a log of function, so we should have a chain rule. And the non-commutative chain rule give us exactly these weights that will appear in the weighted norm, so that we can say the Fisher information is nothing but summation of the dj rho at the rho inverse weight, L2 norm. And this is for the Fisher information. For the spectrum gap, that's for the relative entropy, we can start with the Chi2 divergence from the relative entropy to its continuous expectation, and this is weight at the invariant state, so we can apply the spectrum gap. By losing the gap constants, we go to the energy form, and this energy form use this square form again. We can write it as a summation of weighted L2 norm. And then the only difference with Fisher information is here we are weight on the invariant state, here we're weight on the input state rho. And we can then lose the constants, lose the order constants, and we can switch this invariant state to the state we want, the input state rho, and that gives us the Fisher information, the entropy production. And here, this constant c is an index of the continuous expectation that's defined as the informal of the c, such that rho is marginalized by continuous expectation of rho times the constant c. Okay. So I think I have 5 more limits. So the second proof is slightly more involved. Then I will skip the detail of the proof, but just to show you what's the estimates going to have. So the second estimates, we will rely on the Lie group structure of the generated by the Lindeblad operator. And finally, we can have a lower bound of CMSI constants is greater than the constant C over 1 plus m. M is the number of the unitary that we need to realize the continuous expectation as a unitary design. And the DH is some diameter of the compact Lie group generated by the Lindeblad operator. So this constant is more from the geometric perspective of the Lindeblad generator. And in the proof I present, that's in the joint work with Cambyse, that we'll be able to show that the MSI constants is comparable to the spectrum gap of the generator up to this index of continuous expectation. And if you run the same proof for all the matrix level, we will replace the index by the CB index, which is nothing but just taking the supreme of the index of the continuous expectation tensoring identity on the matrix algebra. And in the primitive case, we will have the invariant space is trivial, and the CB index is going to be the maximal case. This is the largest index we can have. This is just D squared. Hence, we can safely say in all the cases that our CMSI constants is lower bounded by the spectrum gap dividing by times D dividing by D squared. On the other hand, from the hypercontractivity, Castorinaro and Tam, they'll be able to show that the MSI constants can be lower bounded by the spectrum gap over log of the dimension, but this is only for the MSI but not for the complete constants. So it remains open that can we match the complete constant estimate to the same asymptotic order. In the rest of 2 minutes, I just want to mention an application or improvements on the constant in a special scenario in which we can have a tool called Approximate tensorization. So let's consider we have a finite graph that's at each vertex we have a local Hilbert space of same dimension, and the total Hilbert space just a tensor product of all the local system. And the generator is a summation of local generator, and each local generator is acting on the two Hilbert space connecting by an edge. And then we denote the continuous expectation, the basically limits of the semigroup generated by each local generator, and also denotes EG as the continuous expectation of the global generator. So in the exact tensorization case, which means that this local continuous expectation, they commute as a map, then we can have the property, the relative entropy from rho to the global continuous expectation can be upper bounded by sum of rho to each local continuous expectation. And since now we're in the local continuous expectation, we can use the CMSI constant for each local system. And then finally, we can choose the minimal constants, and then we reach that the global CMSI constant is just the minimum of local CMSI constant. This is the way the exact tensorization happens. But actually, we find that even though such condition is not holds, but we can find up to a constant C, this argument still holds. Then more precisely, we'll be able to show if we have a finite connected graph with n vertices and the maximal degree gamma, then for all local dimension D, that's independent of local dimension D, we can have the CMSI constant of the global generator is greater than 1/4 of this loop function inverse. There's a lot of term inside, and then times the minimal local CMSI constant. So you can basically group up the local estimates to get a global constant. One more interesting example is the called quantum CAS model, which is related to the unitary design. This is to take the previous scenario with the complete graph. That's you have graph connecting every two vertices. And the quantum CAS generator is a special case of previous picture. We just choose each local generator as the identity map subtracting averaging of unitary conjugation for some measure on the unitary group. And genetically, we find that the CMSI constants using approximate tensorization technique is of the order 1 over the n. Of course, using this notation, we're subtracting the dependence of other parameters like the local dimension. And we find that this behavior is analogous to the 2 over lambda minus the analogous to the classical CAS model proved by Vignani. And finally, I just want to mention there's more application of our results in quantum Gibbs sampler. This will appear in Ahila's talk later today. And I will stop here. And for that, I would like to thank you.
Okay, thank you, Li, for the nice presentation. Maybe I will ask maybe one two big questions. So maybe I missed something, and this alpha C will also be used to prove any decay properties of the Markov semigroup.
Yes. So basically, this alpha C is to this alpha C is to define as the infimum of all of these decay coefficients for the semigroup tensoring with identity on environment. So it's not only control the decay property of the semigroup itself, but it also control the decay property of the semigroup coupled with the environments in a uniform way. In particular, you can say I have an entangled initial states with some environments, so this alpha C can also control the decay property of an entangled input.
Okay, thanks.
Thank you.
Okay, do we have any other questions?